So today we'll discuss the previous year question, numerical part of Igneous Petrology. First, in the given diagram, the percentage of plagioclase feldspar in a rock of composition X. So a composition X is given here in a triangular composition diagram. We have to calculate the percentage of plagioclase. So first, in a triangular composition diagram, the percentage of any mineral at the vertices it is 100%. And the line parallel to the vertices it has value 0%. That means the plagioclase value here it is 100%. Then on this line, on quartz alkali feldspar line, it is 0%. So as we move away from the alkali feldspar quartz line towards plagioclase, the percentage will increase. Then depending upon how many divisions we have taken, we can represent the percentage of this line. So it will be 20%, this will 0, 20, 40, 60, 80 and 100. So here on this line plagioclase percentage 0, then on this line it is 20%, on this line 40%, on this line 60, 80 and 100. So at X, if you know the composition of plagioclase, it will be 20%. Similarly, we can calculate other percentage also. So line parallel to quartz vertices, that will give percentage of quartz. The value of quartz is 0 here, then 20, then 40, then 60. So the X is in between 60 and 40, so it can be, the quartz will be 50%. So if quartz 50, plagioclase 20, the rest 30% will be alkali feldspar. So alkali feldspar, it will be 30%. So our answer will be 20%. We can also calculate other mineral percentage from this triangular composition diagram. Next, using the rule, phase rule, the maximum number of phases. So what is the phase rule? It is P plus F equal to C plus 2. If you have isobaric system, then P plus F equal to C plus 1. But here it is not given in isobaric condition. So what is given? The maximum number of phases in a 3-component geological system. So component is given 3. Having 1 degree of freedom F is given 1, so we have to calculate the phase. So it will be, phase will be 4 here, phase will be 4. In the given phase diagram, the weight percent of melt at point M for a crystallizing magma of ball composition X. So we have initial composition X, it will start crystallizing from this point, and when it will reach to M point, we have to calculate the weight percentage of melt. So at M we have to draw a tie line to the solidus. So this will solidus, this is liquidus. So by this line you can see the tie line will divide into 2 segments. This is one segment, this is another segment. So the segment that touches the liquidus will give the solid percentage, this will be solid segment, and the segment that touches the solidus will give the liquid percentage. So here we are required the melt composition or liquid composition. So the melt percentage, it will be liquid by liquid plus solid into 100. So the value of liquid segment it is given 3 divided by the value of solid segment and liquid segment will add up to 5 into 100. So it will be 60%. So melt percentage will be 60%. Answer will be 60%. This calcite, quartz, wollastonite and carbon dioxide fluid. So we have calcite, quartz, wollastonite and CO2. It is in fluid condition. Were present in equilibrium during the formation of Cal silicate rock. In the chemical system, we have CaO, SiO2 and carbon dioxide. We have to find out the degree of freedom in the assemblage. So for degree of freedom, we require phase and component. So what is phase? It is physically separable unit. You remember the number of mineral present. All the mineral can be counted as phase. So here mineral present calcite, it is in solid condition, quartz, wollastonite, they all are mineral, so they can be considered as phase. So calcite will be one phase, then quartz will be one phase, wollastonite will be one phase. Then CO2 fluid, it is in liquid condition, that will be also considered as one liquid phase. So there are three solid phase, one liquid phase, so phase is 4. Then comes to your component. So component means it is the minimum number of chemical species that are required to define all the phases in the system. So in this system we have calcite, so which has a composition of CO, CO3. Quartz we have composition SiO2. Wollastonite we have Ca, SiO3. So in all these minerals we have CO2. So these three things or these three chemical species are sufficient to represent or to define all the composition, like Ca, CO3 has CaO, CO2, SiO2 has Si2, Ca, SiO3 also has CaO, SiO2, and then CO2. So these three are the minimum number of chemical species to represent all the phases in the system. So that's why component will be 3. So degree of freedom will be 1. So degree of freedom will be 1. The melt in a binary system, MgO SiO2 contain 89.92 weight percentage of SiO2. So we have a melt in a binary system, MgO SiO2 melt, which contain SiO2, it is 89.92%. If SiO2 is 89.92%, then MgO will be 10.08%. So if all the magnesium is consumed, to form enstatite. So in this system, the amount of magnesium present is all consumed to form enstatite. Then how many moles of this mineral will crystallize from 100 grams of the melt? So if you have 100 gram of melt, then if all the magnesium will consume, then how many moles of enstatite will form? So first we write down the reaction. MgO plus SiO2 equal to MgSiO3. That means 1 mole of MgO, it is producing 1 mole of MgSiO3. So 1 mole of MgO, it is producing 1 mole of MgSiO3. That means the mole or number of mole of MgO present in this 100 gram of melt will be produced that much mole of MgSiO3. So जितना मोल MgO होगा उतना मोल MgSiO3 प्रोड्यूस होगा. So that's why we have to find out how many moles of MgO is present in 100 grams of the melt. So in the binary melt we have 89.92 weight percent silica and 10.08% silica. So we have 100 gram of melt. So 10.08% of 100 gram is also 10.8%. So MgO will be 10.08 gram. MgO will be 10.08 gram. So all the MgO has used to produce MgSiO3. So 1 mole MgO will produce 1 mole MgSiO3 according to the reaction. So जितना मोल MgO होगा उतना मोल MgSiO3 प्रोड्यूस होगा. So we have to find out the moles of MgO. So moles of MgO here is given mass, that is 0.8, and the molar mass it is given 40.03, 40.3 will be 0.25. So MgO is present 0.25. So So 0.25 moles will all consume to produce 0.25 moles of MgSiO2. So question is asked, how many moles of this mineral will crystallize? That is 0.25 moles of this mineral will crystallize if all the MgO will be consumed during formation of answer type. The lazulite generally from the mantle contain 50% volume of olivine. So it contains olivine 50%. The rest being equal proportion of orthopyroxene and clinopyroxene. That means orthopyroxene it is 25%, clinopyroxene it is 25%. So the density it is given in gram per cc. For olivine it is given 3.42, orthopyroxene it is given 3.28, clinopyroxene is given 3.46. So we have to calculate the bulk density of the genolith or bulk density of the lazulite. So lazulite contain olivine, OPX, CPX, they all will contribute their density. So if olivine is 100%, then it has density of 3.42 gram per cc. But it is 50%, so you have to take the 50% of 3.42. Then we have to take the 25% of 3.28. Then we have to take 25% of 3.46, and then we'll add. That will give the bulk density of the lazulite. So bulk density will be 3.42 into 0.5. 50% is given, so we have to write down 0.5 plus 3.28 into 0.25 plus 3.46 into 0.25. So it will be 3.395. So you have to give answer in two decimal places. So we will write down 3.39. So the bulk density will be 3.39 gram per cc. Because here all are in gram per cc, so you don't need to convert anything. So answer will be 3.39 gram per cc. Then the SiO2 value recalculated on volatile free basis on the rock whose major oxide weight percentage is given. So SiO2 value we have to recalculate it. So this is the oxide value present in a rock. So we have to calculate the SiO2 value, or you can say to normalize the SiO2 value. So simply you have to calculate the total oxide percentage, that is 95.72. So SiO2 percentage divided by total percentage. So 45.58 divided by 95.72 into 100. So you can calculate any oxide, or you can calculate normalize any of the oxide by this process. So it will be 47.61%. It will be 47.61%. Then consider the four minerals P, Q, R, and S in a three-component chemical system. So we have a three-component chemical system. So component here is 3. Sorry, the figure for a crossing tie line. So this is a crossing tie line. We have composition X here. The variance of the equilibrium mineral assemblage at X. If you are considering assemblage X, it will contain all P, Q, R, S. It will contain P, Q, R, S. So X contain P, Q, R, S. So all will be considered as phase. So phase will be 4. So you have to calculate the degree of freedom. That will be C minus P plus 2. It will be 3 minus 4 plus 2. It will be 1. It will be 1. Then when a dunite comprising of pure phosphate, so we have a dunite, it consists of completely pure phosphate, undergoes melting. The weight percentage of MgO in the melt. So By duonate, it completely consists of phosphorite. When it will melt, it will completely contain only phosphorite. Only phosphorite. That means Mg2SiO4. So we have to calculate the MgO percentage. That means we just have to calculate the MgO percentage within phosphorite, because it all contain the melt all contain MgO. So in Mg2SiO4 we have 2 moles of MgO and 1 moles of SiO2. So the weight percentage of MgO, it will be weight of MgO, that is 2 into weight of MgO, that is 40.30 divided by 60.08, total weight 60.08 plus 2 into 40.30. So weight of MgO present in phosphate by total weight of phosphate. Weight of MgO present in phosphate by total weight of phosphate. So it will be 57.29. Answer we have to give in one decimal. So it will be 57.2. 57.2. Then a melt containing 900 moles of anorthite and 100 moles of diapside. That means we have 1000 moles of melt. 1000 moles of melt. That undergoes crystallization. So at this point, crystallization will begin. It has 900 moles of anorthite. That means 90% anorthite, 10% diapside. From this point, crystallization will begin and it will start to crystallize. The anorthite will crystallize. So you have to calculate the melt composition, the number of moles of anorthite. Actually, we have to calculate the number of moles of anorthite that crystallize as a melt composition move from P to Q. So you have to calculate the solid percentage or anorthite percentage at Q, because at anorthite we only have, at Q point we only have anorthite. So at this point liquid composition it is given 50%. So at Q you have liquid percentage 50% anorthite. This is your 100% anorthite, and this is initial 90% anorthite. So we have to calculate the solid percentage. So this will give the solid segment, this will be the liquid segment. So I have to calculate solid percentage, that means solid by solid plus liquid into 100. So solid percentage, it will be solid by solid plus liquid into 100. So what is the value of solid? It is 40 divided by 50 into 100. So it will be 80%. It will be 80%. So solid percentage, it will be 80%. So 80% at this point, we say at Q point, we have 80% anorthite, 80% anorthite and 20% is melt. So from 1000 moles of the melt that we have initially taken, 80% is crystallized up to point Q and 20% is still in melt condition. So that means the anorthite, it is 80% of 1000 moles. So it will be 800 moles. It will be 800 moles. So at Q point, anorthite will be 800 moles. Answer will be 800 moles. And at a temperature of 298.15 Kelvin, the free energy change of a reaction del G0 is 19.737 kilocalorie per mole. If the universal gas constant R1 is 1.98717 calorie per degree per mole, then the log 10 of the equilibrium constant K is. So you have to calculate this using this formula del G equal to minus RT ln K, or you can write down del G equal to minus RT log minus RT, sorry, write down like this, minus 2.303 into RT log K. So your R, it is universal gas constant, del G you know it is the free energy, then T it is the temperature in Kelvin, K we have to calculate. So log K actually you have to calculate. So log K it will be, say, del G divided by minus 2.303 RT. So del G it is given 19.737, it is given kilocalorie, we will convert it into calorie, that will be 10 to the power 3 calorie per mole. Then we have minus 2.303 into R is given 1.98717 calorie per degree per mole. Then temperature it is given 289 Kelvin. So temperature it is given 289.15 Kelvin. Sorry, 289.15 Kelvin. So here gas constant it is in degree, so we have to convert the Kelvin into degree. So 19.737 it will become 19737 calorie per mole divided by, so this is 298.15 Kelvin. So I have to convert it into degree centigrade. So because it is in degree, so if you convert it, so you can convert Kelvin into Celsius. So Celsius will be Kelvin divided by minus 273.15. If you convert it, it will be 25 degree. It will be 25 degree. This will be 114.411. It will be 172.509. So I have to round up to 2 decimal. It will be 172.51. So to calculate the difference between XAN, XAB at X point. At X point, the value of albite it is 20%, and see 20, 40, 60, 80, 100, and at X point the value of anorthite it is your 40%. It is 40%. So at this point, the fraction of anorthite it is 0.8 AN. If it is 40%, the fraction of anorthite will be 0.4, and fraction of albite it will be 0.2. So it is given the difference between XAN and XA albite it will be 0.2. 0.4 minus 0.2 it will be 0.2. So answer will be 0.2. So the given pressure temperature diagram show the relative stability range of andalusite, sillimanite and kyanite. The diagram andalusite, sillimanite, kyanite. The difference in degrees of freedom at point X and point Y. So it is a uni-component system. So component here will be 1 at this field. At X point only kyanite is exist. So at X if we will calculate, the phase will be 1. You have to calculate the degree of freedom. Component is always 1. So degree of freedom will be F will be 2 at X. At Y, it is the triple point or it is the invariant point where all the three phases will coexist. So 3 plus F equal to 1 plus 2, component is always 1. So F will be 0. So at Y, F is 0, at X, F is 2. So the difference will be 2. Answer will be 2. Then according to the mineralogical phase rule, the number of minerals that can coexist at equilibrium in a 8 component chemical system with 2 degree of freedom. So according to mineralogical phase rule means degree of freedom will be 2 or more than 2. That is your mineralogical phase rule. So the number of minerals that can coexist at equilibrium in a 8 component system. So component it is given 8. Degree of freedom is 2. So we have to calculate the phase, that will be the number of mineral. So P plus F equal to C plus 2. So phase we have to calculate is 2 equal to component is 8 plus 2. P will be 8. So according to mineralogical phase rule, actually F equal to C minus P plus 2 is equal to 2. This is mineralogical phase rule, where number of component is equal to number of phase. So if it is given according to mineralogical phase rule, you don't have to calculate also. You will know if the component, you will know the number of component, that will be the number of phase. So number of component is equal to number of phase in case of mineralogical phase rule. It is also called as Goldschmidt phase rule. Consider the schematic isomeric temperature composition phase diagram in the binary forsterite phyllite chemical system. So I have a binary temperature composition diagram, forsterite phyllite. There is a equilibrium crystallization of melt L. So melt L, it is crystallizing in equilibrium condition. The weight percentage of olivine crystallize from a melt of a composition A. So I have a melt of composition A which has, you can say, 60% of forsterite. When the composition A at a temperature of T2. So we have to calculate the weight percentage of olivine. That means the weight percentage of solid when the composition reaches at a temperature T2 at this point. So at this point liquid composition it is 50%. 50% pure phosphorate. Sorry, 30% phosphorate. 30% phosphorate. At this point it is 30% phosphorate. 30% phosphorite here. So this is liquidus, this is solidus, this is our initial composition. So we'll join the tie line here. So this segment will give the liquid percentage and this segment will give the solid percentage. We require the liquid percentage in the melt, then we can calculate the olivine percentage. Also we can calculate the olivine percent directly. Take this. This is point. It is, we'll write down in terms of phosphate. Phosphate is 30 here. Then the initial composition is here. This is A point. This is, let's say, T2 point. So initial phosphate is 60. Then the solid composition here is, it is 70. Phosphate 70. So this will be your solid percentage, this will be liquid percentage. The solid segment divided by solid plus liquid, that will give the solid percentage. The solid segment, it is 60 minus 30, it will be 30 divided by 40 into 100. So it will be 75%. So at this point 75% olivine will crystallize. The weight percent of olivine will be 75%. Consider symmetric isobaric ternary phase diagram ABC. So ABC is given here. The diagram which is contoured with isoplates of liquid temperature in degree. So these are contours of temperature. It is given here. So when a melt composition lies at temperature 800 degree, when a melt composition of A lies at temperature of 800 degree, the variance or the degree of freedom is the magma system. Now it is at A point, if it was at 800 degrees centigrade, so it will be completely in the melt condition. It will be completely in melt condition. So because it is represented at 1700 degree from which it will crystallize, it will start to crystallize. So from the temperature above the freezing point, it will be in liquid condition. So component here will be 3, it is a tri-component system. Phase will be 1 because it is in melt condition. So it is isobaric even, so you have to calculate by like this, P plus F equal to C plus 1. So P is 1, degree of freedom we have to calculate, C is 3 plus 1. So degree of freedom will be 3. Then the following isobaric temperature composition diagram, the number of common phases in all invariant points. So this is a ternary phase diagram, we have 2 invariant points, one peritectic, one eutectic. So at peritectic point, A and C are the phases, and at eutectic point, C and B are the 2 phases. 2 phases with liquid, here is also liquid. So 2 solid phase, 1 liquid, here also 2 solid phase, 1 liquid. Among them, the C is the common phase. So the number of common phases, it will be 1. Then the density of a 200 gram gabbro sample. So I have a gabbro sample of mass 200 gram got in the form of Q. Density is given 3125 kg per meter cube. It will be 3.125 gram per cc. So we have to calculate the length of the sample. First we have to calculate the volume, rho equal to mass by. So volume equal to mass by rho, 200 divided by 3.125 gram per cc. So here it will be gram per cc. The answer will be in cc. So it will be 64. So volume will be 64. Volume you know AQ because cube it is given shape. So A will be 4. A will be 4. It is centimeter. A will be 4 centimeter. So it is asked in mm. So it will be 40 mm. A will be 40 mm. The following diagram represents a binary phase diagram, system A and B. System A and B given at atmospheric pressure. If X is the initial composition, which is first B 30, A 70. So initial composition X, it has A 70, B 30. So if X is the initial composition of melt, then the amount of melt that converts to solid when magma cools from 1400 to 1250 degrees. So we have to calculate the melt composition here and here. We will subtract them. that will be the melt percentage that will convert to solid. So first we will calculate the melt percentage at 1400 degree centigrade. So at 1400 degree centigrade, this will be X, and this indicate the solid composition. It is given 10. It is your 30. It is given 40. So this segment, it represents solid and this segment represents liquid. So we will calculate melt percentage. So melt percentage will be your 20 divided by 30 into 100 will be 66.6%. Then we will calculate melt percentage at 1250 degree centigrade. So here the solid composition at 1250, it is this much, it is 25. So initial composition we have 30, and the melt composition at this point it is 75. So this will solid segment, this is liquid segment. So melt percentage will be 5 by 25 minus 75, it will be 50 into 100. So it will be 10%. So at this point melt was 66.6%, at this point melt was 10%. So the melt that lost from this point to this point will be converted to solid. So it will be 66.66 minus 10 will be 56.66%. Will be 56.66%. I have to round up. It will be 56.67%. 56.67% will be the answer. Next, a hypothetical rock contains the assemblage of kyanite, sillimanite, and quartz. So we have kyanite, sillimanite, and quartz. The variance of degree of freedom of the assemblage. So we have to calculate the variance degree of freedom. So there are three minerals here. So component will be 3. Sorry, phase will be 3. Then component, these two have same chemical formula, Al2SiO5, and quartz it is SiO2. Then we have two component here, the two chemical species to required to represent all the phases. So we will apply the apply the phase rule P plus F equal to C plus 2, because it is not an isobaric condition. So P3F component will be 2 plus 2. So degree of freedom will be 1. In the figure below is an isobaric binary temperature composition Px plot. The amount of percentage is given. This point to this point it is given 42%. This point to this point it is given 35%, and this is to the R it is given 10%. So the value of R it is here. A is 90%, B is 10%. The composition of R is 90% A, 10% B, because if it is 100%, this will be 90, the difference will be 10%. So the equilibrium melting of rock R will generate a melt composition L. So you have to calculate the percentage, the amount percentage of the equilibrium melting rock R will generate a melt. So you have to calculate the melt percentage at L point. At L point. So this will start melting from this point, you can say, then it will move like this to this point. So simple, we have to calculate the melt percentage at this point. So this segment, it will give you solid percentage, and this segment will give you melt percentage. So this is your 10% already given, and we have to calculate this percentage. Okay. So this thing is given 35%. This thing is given 35%. So it will be 10 by 35 into 100. 10 by 35 into 100. So it will be 28.57. So we have to round up to 2 decimal. It will be 1 decimal. It will be 28.6%. Yes, also the following figure shows an isobaric temperature phase binary system AB. If P, it is the initial composition, which is, you will say, 60% B. So initial composition we have 60% B. This will take P. This is 60%. The amount of liquid that remains in the system when the liquid cools from 1800 degrees centigrade to 1500 degrees centigrade at this point. So simple, we have to calculate the melt percentage at L2 point. So this will be the solid segment, this will be the liquid segment. So the L2, it is representing the liquid percentage is 20. Here the solid percentage is 70. You have to calculate the liquid percentage. This is your liquid segment. It will be 10 by 50 into 100. So it will be 20%. So at point L2, 20% of the melt will remain. Then clinopyrazine crystallizing from a basaltic magma has SM concentration 24 mm. So it is given the concentration of, you can say, solid of SM. It is given 24 ppm. If the clinopyrazine melt partition coefficient of SM is D. DSM, it is given 1.2. Samarium it is given 1.2. We have to calculate the concentration of SM in the basaltic magma. So you know, distribution coefficient is of concentration of solid by concentration of trace element in liquid. So it is CS by Cl. So concentration of solid, it is given 24 ppm, divided by, we have to calculate the concentration of samarium in liquid, it will be X, and D is given 1.2. So the concentration of liquid, you can say Cl of SM, it will be 24 ppm divided by 1.2. So it will be 20 ppm. Then the given isobaric binary temperature composition Px phase diagram involving solid A and B, solid and B given. It is 1, 2, 3, 4, 5 division. You can write on 20, 40, 60, 80, 100 in terms of B. So in terms of A, we are writing A 100, 80, 60, 40, 20. Accordingly, B you can write. The fraction of melt remaining at point Q. You have to calculate the fraction of melt remaining at point Q for a magma having initial composition P. So you have to calculate the melt percentage. This is a melt segment. So at this point, this is 20, this is also 20. So I will say 50% will be the melt and solid composition. So answer will be 50%. Then the fraction will be 0.5. So answer will be 0.5. So it is aspirant fraction. So you just have to convert the percentage into fraction. So this is all about your igneous petrology question starting from 2015 to 2024.